Hey guys, it's Professor Rourke. I had some question about the yucky, lovely WebAssign question. The last question on 4.7. So sometimes on WebAssign, I think it's sometimes better to think about it almost as like extra credit for some of these, because of just sort of the level of difficulty. But also it's kind of good to be able to see, especially when it can be sort of confusing. So here I am. I'm going to make a little video about this. Hopefully, not too long, but we'll see. Okay. So this is question number 10 on WebAssign, which actually looks like it comes from our textbook. If you're looking at the actual text, physical textbook or the e-text, it's problem 46, which is a little bit lower down on some of the problems. I feel like sometimes, they build in complexity level. So we'll try to keep in mind the same process that we want to use for all of these problems and sort of keep in mind that this could take a little bit more either like algebra or maybe like trig knowledge or whatever than maybe your sort of typical optimization problem might require. But we got this, no matter how yucky or spicy it is. So let's take a look. So it says a fence 8 feet tall runs parallel to a tall building at a distance of 4 feet from the building. Thank God they gave us a little diagram because that whole sentence there really is a little tricky. So there's a building, and then 4 feet after that, there's an 8 foot tall fence. And then it looks like they actually put a ladder and they laid the ladder down on the fence, which I don't know if that's a good idea, and onto the wall. So, okay, sure. So it says, what is the length I have to scroll here a little bit, in feet of the shortest ladder that will reach from the ground over the fence to the wall of the building? Whew, it says round your answer to 2 decimal places. All right, so that's a lot going on there. So what I wanted to start out with is I went ahead and made a little whiteboard with this drawing just to kind of start us out there, and then we'll go from there. Okay, we'll see how things are feeling. So let's see if I can pull up this. There it is. Okay. So yes, here we go. All right. So um, first things first again, this is like I copied pretty much what they gave us, but they had a little bit more detail with like grass color and the wall, but same idea, right? And so what we always want to do first, even if it seems overwhelming, I think it always just sort of helps me to first think about what is the problem even asking us to do, because it's not always the most clear. Okay. This is also like a new Zoom whiteboard, like it's been updated, so some of it gets a little bit much for me. Sometimes I'm just used to the old, just very simple whiteboard, no scrolling, but this is good. It was good, right? Okay. Anyways, okay. So the first thing I want to do is sort of again conceptualize the problem. This means we want to figure out like what are we optimizing, because that is really what we are going to have to come up with an equation for. Okay. So I know there's a lot going on here. There's a lot. I don't know. Thankfully for that diagram, but even then, it's a lot. So okay. Again, there is this fence and a ladder and a wall and the ground. So I feel like there's just a lot of pieces, right? But they're telling us that the ladder is 4 feet from the wall. Okay, so that's why we have this piece labeled as 4 here. And then they tell us the ladder is 8 feet. So I went ahead and just moved it like right next to it just to kind of see that a little bit better. And then we have the ladder and the wall. And it's like, what are they actually asking us to optimize? It says, what is the length of the shortest ladder? Okay, so they're actually asking us in a complicated way, but still asking us, I guess. What is they want us to what is the shortest ladder? Okay. Is length of the ladder, I should say. That's kind of almost like that's actually like in this right triangle. If we think of these as right triangles, right, that sort of almost looks like the hypotenuse, right? If we thought about this as like one big triangle. And that's, I think, kind of like there's probably more than two main ways, but I feel like there's two main ways to sort of approach this problem. One way is to treat this sort of like as a bigger triangle and a smaller triangle, and use similar triangles to try to solve. I'm not gonna lie, that way, I know I've done this way before, and so you can too. It does get a little bit dicey when we're trying to actually solve. It's a little bit it's a little bit yucky. Okay, so you can do that though. If you use similar triangles, you can do that. I'm going to show you what I think is actually a little bit easier using our trig knowledge. But again, I know there's almost always more than one way to solve these. And so if you want to try using similar triangles, by all means, you can go for it. Okay. All right. So what I'm going to try to again present to you is a way that we can solve this using trig, because we're really trying to again get the shortest length of the ladder. And so one way of thinking about this is actually the ladder could be thought of as two separate pieces because of this 8 foot tall fence. And they told us again it was 4 feet away. We can sort of use that to think of this as two different triangles, right? We could think of this as a little mini right triangle that goes from the top of the fence over to the wall, which we know is 4 feet, right? We don't really know how tall this is, but we also don't really know like what the this length right here would be. I'll say like this top length, maybe top triangle length. This is again one way we can sort of think about this as is two separate triangles, but not really similar triangles like you could do. We could set up similar triangles and try to think about it using proportions. So that is an option again, but that's not the way we're thinking about this. We're thinking of this as two separate triangles, but not so much of similar triangles, just with trig knowledge. Because again, we could break that up into one right triangle, and then we could break this up into another right triangle. And we know from this right triangle, essentially, that once again, we do not know like the length of the hypotenuse. So these are really like two different lengths, right? That we could come up with an expression for and then just kind of put them together. Okay, so I put these sigma angles on the top. I'm not gonna lie, you could also put them on the bottom. You could instead, just to kind of make sure we're on the same page, we're sort of just selecting where we want theta to be. Theta's kind of irrelevant really for these problems. But you could pick theta to be on the bottom as well, the bottom angles. But let's just go ahead and take a look at what we have going on here. Okay, so I'm going to try to write what the formula is going to be. It's going to first be, it's sort of all, I feel like it's kind of, right where we left off in the first one is like, what are they asking? Now we're going to try to answer, like, can we write a formula for the length of the ladder. And we don't necessarily need to worry right now about getting it in terms of one variable, but we will do that next. Okay. So again, this is very a complicated version of the type because I think of again of the triangle components, but whether or not we're talking about triangles and ladders or we're just talking about like the perimeter of a field or we're talking about the material used to make a box, you're always first going to just try to come up with the formula for like what are we actually trying to optimize, and then we'll use the extra other information to sort of try to get it in terms of one variable so that we can then take the derivative of it. Okay, so for now, again, it doesn't look great. I know it's gonna look hopefully better at some point, but I'll go ahead and call it L. I don't know for the length. Ooh, that's a highlighter. That's why that looks like that. That was crazy there. Wasn't expecting it to look like that. Okay, let me try that again. Okay, so I'm gonna go ahead and say L for the length of the ladder. And that's going to say like, just going to say it now as like the top length, which I know isn't really the most mathematical, but plus the bottom length. And so I'm going to use these as two separate triangles, and then I can think back into my lovely knowledge of trig, which again, I know can be a little scary, but it's okay. We're going to make it. So let's focus on the top length. I'll just draw a separate triangle down here, which may or may not help. Okay, we are trying to essentially find out what this length is right here, right? We don't know what that is, but we do know that this is 4, right? We do know that, so that's, something. And then we had this drawn over here as this angle. So what we could do is then try to write an expression using trig. And so you're like, okay, wait, let me think about this. What trig expression could relate essentially the hypotenuse? And then this angle we have hanging out here. And then it looks like again, the way I drew it, this is the adjacent side. If I don't want to like make it too confusing, but we could have um, instead drew the angle on the bottom because we're kind of just picking it. But we could do that. Okay, so right now, the way I have this drawn, I have the opposite side, and I also have, I don't know what the hypotenuse is. Okay, so I can call this maybe X, okay, instead of question mark to kind of make it a little bit more consistent, maybe. Um, and so you can pause a second and think, what trig function could I use with these pieces of information? Okay, so again, we have the opposite side and the hypotenuse side. So hopefully you're like, okay, so SOHCAHTOA type thing, right? So sine of theta is opposite over hypotenuse. So we could have like 4 over x, right? Again, which I know this is sort of the piece that makes it think more complicated. But I don't want I don't want it like this. I actually want it, I want to solve for x in terms of theta because I think I'm going to be able to do the same thing for my bottom triangle. So I can have like two different expressions all in terms of just some theta angle, right? So let's see, we have x equals 4 over sine theta. So I could leave it like that. But I feel like, again, thinking about that, we're probably going to take the derivative at some point, right? I might as well make this the easiest as possible. Okay. And so whenever I have like something over sine theta, you want to be thinking like, oh, actually, 4 over sine theta, that's actually the same thing as 4 times cosecant of theta. That way we just have like, we'll take all the help we can get. Okay. So what I came up with is that the top length, if I pick this angle theta, um, this would be equal to 4 cosecant theta. And then I can do the same thing for the bottom length. Remember, this is the same angle. Those are equivalent angles. All those, I know triangle knowledge can be a little bit crazy, but this is my this is my bottom triangle now. And I know that from this, I'll just put like keep this as a question mark from now. From the way I have pulled out and I just kind of copied again this triangle that I got from right here. I know that this side, the piece, the fence or whatever it is 8. It's the same angle as the little triangle we had from up top. And we don't, again, know the hypotenuse length. So then we're like, okay, wait, let me think about this. What trig function relates the adjacent side to the hypotenuse side? So go to a cosine, right? So for this one, we could say cosine theta. So SOHCAHTOA is adjacent, 8 over hypotenuse, which again, I'm just going to call it x for now, but it's not the same x. It just doesn't even really matter. It's the same. It's like whatever that length is. Okay. You can call it B for the bottom length or L for like little L maybe instead of big L. Okay. And then we could be like, oh, okay. So x is actually equal to 8 over cosine theta. And then same thing as before, we're like, okay, I'm probably going to have to take the derivative. So like, I'd rather maybe not have like over cosine x. That doesn't sound great. Oh, theta, I'm sorry. So like 1 over cosine theta is secant theta, right? So then we could just rewrite this as 8 secant theta. Okay, whew, I know it's a lot, but I feel like, again, that's sort of like the key to unlocking, I think, how to solve this problem in the easiest way is to think about this as, ooh, I went to the highlighter again. Think about this in terms of trig, but again, you could solve this using similar triangles if that's what your heart is asking you to do. It's just that you're just going to go down a different rabbit hole of solving. I think the harder part about that way is we kind of get a complicated polynomial type of situation inside of a rational, which is okay. But I'm just going to go down this. I'm going this way. Okay. So ooh, now what? Okay. So first of all, we do know that these angles, I know this can be helpful because there's so many once we take the derivative, we just want to kind of keep in mind that we're not talking about like all the possible angles of the world. All of these angles are less than 90 degrees. So we probably could just kind of put out there, like just so we ever come down to it, like this theta is not going to be more than 90 degrees. It's not going to be 180 degrees. It's going to be between 0 and pi over 2, right? So, okay, great. Now let's go ahead and take this derivative because again, we got to take the derivative so we can set it equal to 0. So I'll call it L prime, or you can call it the derivative of L with respect to theta, whichever direction you want to go. All right, cosecant. What is the derivative of cosecant? I know it's a little bit messy. So the derivative of cosecant is just cosecant cotangent, negative cosecant cotangent, right? So I'm going to just rewrite this as negative 4 cosecant cotangent. Okay, at least I don't have to worry about like product rule and stuff. And then what's the derivative of secant? It's just secant tangent, right? So I'm gonna say plus 8 secant theta tangent theta. Okay, cool, cool, cool. That's my derivative. Looking all right. Ugh. And then we have to now set this equal to 0 and solve, which again I think would be what some people would be like, but if it wasn't trig, this would hopefully not be as scary, right? Maybe you have a quadratic or some sort of rational where you set the numerator and denominator, graph our derivative, and to try to get our estimate, get our value from the derivative graph. Okay. Depending on what section you're in and things like that, if this was a type of question, I would be fine with that because I think the trig knowledge required is quite deep. Okay, so what I'm going to go ahead and do is I'm going to share with you the Desmos graph just so you can get an idea. You can definitely graph this in your graphing calculator. It's just on the computer, it kind of looks a little bit better, I think, on Desmos. Okay, so I went ahead and entered in the actual derivative equation into Desmos, and I'm just looking again for where it equals 0. Now, because this is such a lovely trig equation, there are quite a few places that this graph intercepts the x-axis, but we only really want the ones that would apply for our problem, right? Because remember, again, we said before, like our angle that we're talking about, it's not going to be anyway, it's not going to be greater than 90 degrees, right? Which is like the equivalent of pi over 2. So we're looking for an angle between 0 and pi over 2. And I think this is the one we're looking for. Okay, so you could, again, take a while to try to solve for this, for theta. But I think because of just the amount of background trig knowledge, like if you want to maybe challenge yourself to see if you can get that, I'm all about it. But I feel like if the trig knowledge so far was enough for you, I would maybe recommend just using your graphing calculator or even something like Desmos to get the solution, right? Because again, our whole answer is supposed to be in terms, it can be rounded anyways. So, I feel like it's kind of like a win-win. Okay, so there are a lot of places where this derivative graph equals 0, but the only one that we're really going to focus on is the one that is actually between 0 and pi over 2, which let me see if I can get my pencil back over correctly, is the 0.67089. Okay, so that gives us the angle, which how does that help us? Not really at all. Okay, this doesn't this doesn't really help us. This can help us though. We're getting close because they want to know again the shortest length, and this is where this is the critical number, the only critical number between 0 and pi over 2. So technically we could do like a quick little second derivative, but I think we've suffered enough. We can also tell from the derivative graph that it was going from negative to positive, right? So that is telling us that the original graph is decreasing and then increasing from this point. So that's another way that we know that this is going to be the minimum. Okay, it's not a maximum, which, most times it's going to be whatever the problem's asking you to find, but it's always good just to kind of check. Okay, so last but not least, we actually just want to answer the question, and the question asks for what was the shortest length. So what I'm going to go ahead and do here is I'm going to go ahead and say 4 times cosecant of that lovely number, that lovely angle, 0.67. I guess I'll just keep all the accuracy for now, just in case. I don't want to have any rounding issues right at the end. That would not be ideal, right? And I don't know why I put so many parentheses there, plus 8 times secant of that same value. Okay, if we just go ahead and take out our graphing calculators, we can get a good estimate. Just make sure on your graphing calculator that you are in radians. That's going to be important. Okay, and so just using my calculator, again, just double check that you are in radians. It's a little bit ugly, it's fine. I get L equals 16.6. I'm gonna go, I'll say 4.8 for now, because I can't remember what the original instructions even asked us to round to. I feel like we've been through so many things together already. Okay, so just to recap again, I know it got a little bit dicey with the trig information, but I don't think that's how I'll finish my steps. So first, you conceptualize the problem. What are we optimizing? Then we give the formula for whatever it is that we are optimizing. The key piece where I kind of we went off over here, I would say would be to use, the extra information that includes that the it was 4 feet away and the ladder was 8 feet tall, to write the formula in terms of one variable, which was for this case an angle, which didn't even have to do really with honestly like the problem, but it was part of it was like the connective tissue that got us there. Okay, and then once you are able to get that in there, that's what we did here. We're going to go ahead then and take the derivative, right? And then from there, you set it equal to 0 and solve. Again, I know this one was quite gross. The ones that I would maybe ask you to do like in a normal class time would not be nearly as gross. So I just told you that I would recommend maybe just to use technology, but if you want to challenge yourself to try to solve it using our trig knowledge, you're more than welcome to do that. Once you have your critical number solved for, you want to make sure you use that to actually answer the question, which here was to come up with the lengths of the ladder. So I would say I just had to round to the near 2 decimal places. So we would say 16.65. Okay, so again, whoo, that was something. That was a road that we went on together. But wow, this was again. I think the problem with this one is just kind of hard to feel confident, on some of these. And again, you can actually solve this in a completely different way. Thanks, trig. I feel like there's so many ways we could solve it. Maybe using similar triangles. So if you solved it using similar triangles, definitely let me know, because I always love to see the different ways that we can solve things, or if you even have a different way to solve it. But even though the trig is a little bit dicey, I do think setting these up as using the trig, just the simple sine, cosine, tangent, and then busting out secant, cosecant, cotangent just to get the distance, is actually the best way to go, even though solving trig equations might not feel like the best way to go. Okay, thank you guys so much. Please keep me posted. Let me know however I can help, and I'll be posting some stuff from 4.8 soon. Okay, thanks.